So what I will do to start with is to give you a little bit of refresher on some of the many body techniques and concepts and ideas that we will need along these lectures in DMFT. Really, of course, I'm not going to give an entire lecture about many-body physics in 3 hours. I mean, that's of course impossible. So what I have done is to select a few topics which are useful and also some topics which, from experience, we know leads to some confusion when people learn and do DMFT. So most of the material I'm going to present this morning is quite standard, not all. Some of it may be more recent, so some of it you already know, and some of it you don't. Please ask questions. This kind of lecture is always delicate to give because I don't exactly know, what you don't know at this stage, so don't hesitate to interrupt. And for that reason, I will give it on the board because it's more interactive. So Michel, you help me if you see questions, because I can't see always people. So the question is, where are we going? What are we going to do in this school? We are going to learn about quantum embedding techniques, meaning DMFT and extensions. And really, if we look at solid-state physics, traditional standard solid-state physics and electronic structures, typical notions, which we will see a little bit, I will refresh you a little bit for metals, is Fermi liquid. Okay, I need to get used to this. I don't want to change the size. I didn't know. Okay. Okay. And density functional theory. And in all of these are the 2 pillars of the theory, the classical theory of metals. In all of these, we consider typically an electron that moves into an effective potential, or we work, more importantly, in K-space. We work in terms of bonds, in terms of quasi-particles, in terms of interaction between these quasi-particles, etc. In the DMFT territory, as you will see, what we are going to do is to work with a different framework and a different idea, which is to take an atom into an effective environment, meaning free electrons bath, an atom with all its interactions. So we are going to have a different view of the solids by really looking at it as a collection of atoms in an environment. So that's the idea which we are going to build progressively, and I will present it tomorrow in the lecture. And to do that, I need some components and some building blocks to do all of that. So really the outline, the things that I really need are 2 things. The first one is green functions. So I will start with an hour about some basic facts about green functions, retarded green functions, self-energies, and so on. And the second part, that will be the last part of today's lecture, hopefully, or maybe part tomorrow, will be a quantum impurity problem. Okay. So these will be the two parts which I'm going to give. So let's start with green functions. So I think it's plus. Or? Yeah. Okay. So first, we are going to solve the many-body problem, which means that we are going to use the second quantized formalism everywhere. So let me fix my notations immediately by defining the canonical operators, CA, dagger, and CA, the creation and destruction operators. We know that if we have an Hamiltonian, which in general is written in the first quantized as a part H0 for each particles plus an interaction part, for example, the Coulomb interactions, we have two categories of states. We have the one-body states, which I'll denote like A, which are, for example, eigenstates of the one-body part of the Hamiltonians. But what we really want to manipulate is the n-body states in their Fock representation. For example, that we are going to have on this form A1, An, where we have a states with n particles of state A1, An, created by creation operators, CAR1, CAN dagger, on the vacuum, this being 0 being the vacuum with no particles. And we know that these, of course, obeys the Clifford algebra. So we're going to express everything in terms of C on CAs. What's important is that we are going to manipulate states with different number of particles, n particles, n plus 1 particles, n minus 1 particles. In all these notations, A here is a multi-index, meaning it can be a position, a momentum, a spin, or anything, or any combination thereof. And the last operator, which I will, of course, use a lot, is Na, the number of particles, C dagger A, Ca. So these are, basic notations. I'm sure you have already used that. It's standard techniques. So just to fix the ideas, I'm going to work systematically in the grand canonical ensemble. Meaning I fix mu, the chemical potential, and the number of particles n fluctuates. So we're going to have states with n plus 1, n minus 1, n plus 2 particles all the time. In practice, of course, we'll fix the average density and compute the chemical potential according to it. In all what follows, I'm going to consider the Hamiltonian H prime, meaning the n-body Hamiltonian minus mu times the total number of particles. That's the number of particles. And because I am on the board, and it takes a lot of time to write everything, I'm going to drop the prime everywhere, just to simplify notation. So when I will write H, you should read H minus mu n. I'm systematically going to work in the grand canonical ensemble. All right. Good. So again, matter of notation. The simplest model we are going to look at is the Hubbard model. Who has already seen the Hubbard model? Almost everybody. Okay, fine. So that I don't need much to say. I'm just going to write it once. We have the sum over a non-interacting part, maybe with spin sigma, plus sum over all the sides of no, there is only one. Ni up, Ni down, where we have a lattice, let's say, for example, a square lattice, and site I and j. And epsilon k is the Fourier transform of the hoppings between different sites. That's a non-interacting part. Would be simple free electron problem. And the local interaction U, no. Okay, these things just change the size, which I don't want to. No. Anyway, to stop this. Okay. On each side, you have an interaction U. That illustrates a little thing which we are going to do quite often. The creation operator can be either on site R or in K-space, related by the standard Fourier transform, K in the Brillouin zone, e to the IK. So I can erase like this? Great. R times CK. Meaning we will be, from time to time, switching bases in the C space. That's an easy example of it. And since I am finishing giving my notations, in all what follows, the sum over the Brillouin zone of 1 is going to be 1. I normalize, I put the normalization into the sigma symbol, just to simplify. So this model is, of course, a completely unrealistic model of a solid. It's, interaction, of course, is not like that. But we will use this in the first lectures, in the first day tomorrow, where we are going to develop DMFT on models. After that, on Wednesday, you will be moving on and doing DMFT and generalizing to realistic materials with DFT plus DMFT in various ways. And all of this will culminate on Friday, where you will see the cutting edge of the methods, I mean, the frontier of the methods, I would say GW+EDMFT. All right, so they were just starting some notations and warming up. I guess there's no question. Good. Now, I can start really part I wanted to do. Let me start with green function. Okay, so now I'm defining the retarded green function in the following way. For any operator x, I'm defining average of x equal to 1 over z times trace of e minus beta h times x, where z is equal to the trace of e to the minus beta h. That's a partition function. Again, this is a grand canonical ensemble. And, therefore, the retarded green function will be defined as GAB, retarded, as a function of t, equal to minus I, theta of t, that's the Heaviside function, times the average of the commutator of CA of t, CB dagger. Oh, why is it changing? CB dagger of 0. That's the definition. Well. Okay. So that defines the retarded green function. That's a T here. Okay. So it's an important object which we are going to see all the time, so it's important to understand the definition well. Here we are talking about, in real time, we're talking the anti-commutator of the C and the C daggers, and of course average both quantum mechanically and thermally, okay? Because of this. Of course, that's at finite temperature. Getting used to it. Okay. T bigger than 0. At 0 temperature, this, of course, is replaced by the average in the ground state. since I'm at it, and in order, now we can define the spectral function. So the spectral function AB of omega is going to be defined by minus 1 over pi, imaginary part of GABR of omega, and the Kramers-Kronig relation as a function. To invert the relation is given by this relation here. And just for completeness, and just to be clear, my convention for Fourier transformations will be this. So that's a very important object which we are going to look at in various forms. The spectral function, the imaginary part of the retarded functions. In a translation invariant system, for example, we have A equal B equal K. We have a function A of K of omega. Okay? Questions on these notations? Okay, good. Can I just let me know if I switch too quickly because I need to write, but you can't see the previous ones. So, yeah. So that's just notations and beginning. The other object which we'll use is the local Green function, which is defined as G log retarded equal to sum over K of G K retarded over, of T or of omega. That will be an important object which we will see and manipulate later. All right. Now, these are definitions. What we are interested in, what I really want to do with these Green functions is to do the following. I want to show which information they contain, and more importantly, how to read information from it. DMFT is a method that is written in terms of Green functions. It's exactly like DFT is a method of the functional of the electronic structure. DMFT is a functional of the Green function, in fact, the local Green functions. So it's very important when you will do calculations to be able to extract from Green functions and from self-energies the physical quantities, physics that we can see, recognize a metal from an insulator, for example. So that's what now I want to show how to do. So the first thing to be reminded of is the Lehmann representation. Just to have an idea, who has seen the Lehmann representation before? Okay, almost everybody, not everybody. Okay. So I'm going to do it in the simplest case at 0 temperature. So at 0 temperature, the average of X is just the value in the ground states, and in the translation invariant case. So the Lehmann representation says that AK of omega, the spectral function, can be represented by the following formula. Sum over A, average in the ground states, CKA squared, delta of omega minus EA plus sum where A and B are many body states which are eigenstates, in fact, of H with energy EA and EB. So, okay, there are two aspects of this formula. First, I'm not going to do a full derivation on the board. Some of the derivation have some notes. If people are interested, we can gather the notes afterwards. It's not very interesting to see all of this. I just will give you an idea how you do that if you have never seen it. But first of all, okay, since I need space anyway, can I push and just use the, can I just push it like this? Yeah. And do a little bit, but that's still the same page, right? Yeah. All right. So how do we derive this? I mean, so the derivation, again, the idea, you just insert a complete basis of states in, for example, the commutator ck of t, ck of 0. You will have a term like this in the ground states. And you insert here the sum over all states over A. And you use the fact that they are eigenvalues of the states and do a Fourier transform. Okay? So that is completely straightforward. There is no more transformation, not any other transformation than this. So that's the formula. So what's interesting is to try to understand a bit what the physics of this is and what does it tell us about the function. Okay, can I cut that? Yeah. Let me try something. Yep. Can I paste it somewhere? Like this? Okay. That's very unsuccessful. Okay, thank you. No! I don't want that. Sorry about that. Yes, voilà. So I just want to use this formula again. Okay, thanks. Need to learn how to use this board, but okay. So two cases. If the frequency is bigger than 0, you see that only the first term will contribute, meaning omega is equal to EA. Of course, because EA on EBs, which are the energies of the states, are positive. I forgot to tell you that I took the convention that the ground state energy is 0, but I just realized. So when we have omega bigger than 0, we have the fact that only the first term will contribute. Omega EA is positive, which means that A is a state with the number of particles in the ground states plus 1. So you're going to have a particle excitation. If omega, however, is negative, only the states with omega equal minus EB will contribute, and therefore B is going to be a state with n ground states minus 1, so it's a whole excitation. Okay? So if I draw a picture, yeah, okay, now I understand, of these. I will get something like that. AK over omega as a function of omega. Here I will have the first one, the particle excitations, and here I will have the whole excitations. So all of these are transitions between states, between the number of electron in the ground states, n ground states, plus 1 or minus 1. Okay? And of course, this can be seen experimentally in the angle-resolved photoemission spectrum, but I have some graphs of that. I will show them tomorrow because switching between the board and the slides is a bit more difficult than early anticipated. So that's the Lehmann representation of the spectral function and its physical interpretation. Questions? Clear? Obvious? Okay. Let's continue. Two examples, which I will basically leave you as an exercise. They are very simple examples, but we will reuse in the following. The first one are independent electrons. So the first part of the Hubbard model. Ça fait minus mu n. Here I put explicitly the mu because I will use it a little bit. So we are talking here about having a bond energy which is filled up to the Fermi level, right? With a Fermi surface. And the point is that the examples to show that the spectral function AK of omega is simply a delta peak, delta omega plus mu minus epsilon k. Or say it otherwise, that the Green function retarded as a function of omega is equal to 1 over omega plus mu minus epsilon k plus I0 plus. So that's a little exercise for you, if you have never done it. How do you prove this? You can do it in many different ways. Let me just give you a hint how we do that. You look at the Lehmann representation that you had before, and you look what are the excitations that you have above the ground state. So there are two of them. I'll make you a little picture. The A1s, the B1s. So the first one consists in putting an electrons at a higher energy. So the EA, the energy that you're going to have here is, if that's at value k, epsilon k minus mu, because we have this term here and this term here. So we add an electron here. Because we are above the Fermi surface, this is positive. And you can replace into the previous formula, and you'll find that indeed it's consistent with this result. The other excitations which we have here is the hole, and I'm now going to try to have colors. Where is it? Yep. We're going to make an electron hole somewhere here with an energy EB, which is equal to minus epsilon k minus mu, which is again positive because we are below the Fermi surface, and you can check that if you report this into the Lehmann representations, because of the signs and everything, you'll get exactly this result here. So it's a little exercise which is good if you have never done it, just to understand the structure of the Lehmann formula. Okay? Good. That's the example number 1. The example number 2, which we will reuse a lot later, is the Hubbard atom. What is the Hubbard atom? It's just one side of the Hubbard model. So I will write it in this way. Hamiltonian equal epsilon d times n up plus n down plus u n up, n down. There's no mu n because it's absorbed in epsilon d. I rename the chemical potential as epsilon d. This is a very simple state, a very simple problem, which is in fact very useful when you try to understand impurity systems. This is a piece of an impurity system. It has 4 states, which are the following: no particles, not equal, with an energy 0. You have the 2 states with 1 electron, with an energy epsilon d, and you have the doubly equal states with 2 electrons, with an energy 2 epsilon d plus u. Okay? And therefore, you can compute all the transitions. So in the regime where the ground state is this manifold, an electron up and an electron down, which corresponds to, if you look at it in a regime where epsilon d is negative and 2 epsilon d plus u is positive, that's called the local moment regime in an impurity. You will have a ground state with 1 electron, and therefore the transitions that you will see in the Lehmann functions are the transition from these states to the 0, removing the electron, or to the doubly occupied states, meaning adding an electron. As a result, your spectral function will look like something like that. 2 peaks, 2 delta peaks, as a function of frequency at epsilon d, negative, and at epsilon d plus u. Meaning the difference of energies between this state and this state, and the difference of energy between this state and this state. Okay? So it's a sum of 2 delta peaks. Well, I can write it, but it's just the sum of this peak divided by 1/2. Okay? In the special case where epsilon d equal minus u over 2, which is a particle hole symmetric case, then the function is symmetric Yes. Like this. So in that case, your spectral function is just a sum of two delta peaks. We will see that coming later. It's really the first baby ingredient which we will need later. All right. So that's the spectral function. Now, questions on this? Still okay? Fine. Okay, that's defining the spectral function, understanding what you have in it, and doing a few examples. Now, what I want to do is to do a little bit of Fermi liquid from there. So let's look at the spectral function. Oops. Okay, so let's look at a non-interacting case. Well, I gave you the answer before. A k of omega is equal to delta omega plus mu minus epsilon k. Which means that if I look at a free electron system as a function of kx and ky, and I look at a Fermi surface, I look across the Fermi surface, for example, a couple of points like this, my spectral function, if it wants to, yes, is going to be peak. Maybe I should use another color. A peak that will disperse progressively if I look. So 1, 2, 3, 4. 1, 2, 3, 4. So if I change the position in the Fermi surface, I will have one peak that will cross the Fermi surface, cross the Fermi level here at omega equals 0, as it should. Well, that's a non-interacting case. Now, what happens when we put interactions and when we are in a Fermi liquid? So, Fermi liquid, there's an entire theory of it. What I'm really interested in here is to understand the quasi-particle peak and how we're going to extract its characteristics from the Green functions, therefore, from everything that DMFT is going to produce. So, in the Fermi liquid, we have the following sketch. A k of omega. As a function of omega, we have something, then a peak, whatever. We will have a quasi-particle peak. Here. And the point is, that's the whole theory on the Fermi surface, is that in the Fermi liquid, this peak has different characteristics. First, it has a position, which is epsilon k twiddle. It's renormalized by interactions. It's not the one of the bare interactions. And it has a width here, gamma k, which is the quasi-particle lifetime. Well, the inverse of the quasi-particle lifetime. And it has also the area of the peak. That's zk. That's the quasi-particle residue. And the point of the Fermi liquid theory is that when your peak, I didn't touch it, yeah? When the peak goes closer and closer to the Fermi surface, the peak goes narrower and narrower. When you're going to cross the Fermi level at omega equals 0 here, the peak becomes very, very thin and then increase again. The point is that the lifetime gamma k is proportional to epsilon k tilde minus mu to the square. Right? So the spectral function encodes the properties of the quasi-particle in the Fermi liquid in this way, because if we know how to if we understand the structure of A, we can extract the quasi-particle residue, the lifetime, and as we will see, the position, the renormalized position of the Fermi surface. Question on that? That's a bit more advanced, right? That's Fermi liquid theory. No questions? Yes, question. No, no, sure.
Why don't we call it quasi-pole residue, because it's below the omega? Why don't we call it quasi-pole residue or
quasi-particle residue?
No, in the sense that it's less than omega equals 0, like a whole excitation.
Yes, but it's, naming. Yeah, you're right. It's a whole excitation and then particle excitation. But yeah, it's called quasi-particle residue. So I can, that's, how it looks like. Just to have a slight different view of it, which goes to the physical idea about the Green functions. The Green function is basically an overlap, because you start at time 0 by taking C dagger on the ground state. Then you time evolve it, right? And then you are going, that's going to be some state, phi, of t. And phi of t, because of interaction, is not simply a phase times C dagger t ground states. But the Green function, if you look at the definition, is proportional to phi of t, phi of 0. Meaning you create an electron at time 0, you let it evolve, and you look at the overlap at a later time with the initial state that you would have. And because of interactions, the state that you have created decays, and it's not the same as the one you started with. Meaning this thing decays, and it decays exponentially minus gamma t, which is a lifetime. But there's, of course, an additional term. It just decays, but it also oscillates, as it should. So if you look at this Green function, you will see that the Green function looks in time like something that oscillates and then decays, right? And the closer you get to the Fermi surface, the smaller gamma is, so the longer the lifetime is, and the more oscillations you're going to see. Because gamma goes to zeros like the square of the position, and by the way, I should have said it, that's a famous result by Landows in the 1950s, the first paper on the theory of Fermi liquids. Then the closer you are to the Fermi surface, the more oscillation you see, and you're going to see. So the closer you get to your Fermi surface in a Fermi liquid, the closer it looks like an independent electron system. That's the key of the ideas with the correction that we have seen. So the green function, the spectral function, contains all the information which we want to have from a Fermi liquid, Z, gamma, and so on. Now, in order to proceed, we need to introduce another quantity which is more suited for that, which is the self-energy. So I'm going to remind you about the self-energy. I'm switching too quickly, just you stop me by raising your hands. Yes? No? Okay. So the definition of the self-energy, sometimes it's a bit... The retarded Green function inverse is equal to the retarded Green functions without interactions, inverse, minus the self-energy. This is not non-interacting. In general, this equation is a matrix equation because G is a function of AB, C dagger A, CB, so it's a matrix equation. Of course, in translation invariant space, it's just a function of K, it's diagonal in K, but that's a definition of the self-energy. So in a translation invariant system, we'll have Gk of omega equal 1 over omega plus mu minus epsilon k minus sigma k retarded of omega. So the self-energy is going to encode all the corrections that we have compared to the bare Green function that we had before. In the bare case, this is I0 plus. And in fact, this quantity encodes the quasi-particle properties exactly, as I will show in a minute, and is more precise than looking at the Green function. So when we are going to look in DMFT, we are going to make approximations for the self-energy that will be a central quantity, and of course then we'll look at it in the Green function. And it's very important in many of the calculations to look at both quantity, as we will see during the lecture later. Yes, 2 questions. Well, you're first.
Is this the retarded Green function or like?
Sorry, yes. At the moment, they are just the retarded ones.
As a silly question, is there any motivation or intuition for the name self-energy?
Oh, yeah, it goes back. It goes back to the old days of quantum electrodynamics, what it was supposed to be. I forgot, a kind of, renormalization of the energy of the particles, but it's just a name.
Okay, just an older context.
Yes, it's there since the beginning of field theory, so that's the reason. The thing you should really view it here is it's like a lifetime. The imaginary part is like a lifetime, and the real part is going to be renormalizing this. So it's just,
Just how far away you are from the...
Yes. It's how far away you are from the non-interacting part, but because the non-interacting function is a delta peak, you need to approximate the inverse. Because, a delta peak is, you can't move it easily, so you need to approximate it here in this inverse form. And as I will explain in a second, this object is particularly well suited in a metal or in a Fermi liquid where we are close to an independent electron problems. And it's not very well suited for insulators, where it's going to behave badly because, the starting point is not correct. Of course, I'm not going to use diagrams here because I don't know, how many familiar people with the diagram techniques. But these objects have diagrammatic representations as well, that you can find out systematically in perturbative expansions. But that's not exactly what we need. Okay, more questions? Yes. So now the question is, it's great to define the self-energy. As we'll see, we will be able to calculate it. Then what can we extract from it? Okay. So self-energy in a Fermi liquid. So I am going now to consider a Fermi liquid at a frequency and a temperature less than something, which I will call a coherence energy or a coherence temperature. I will discuss what it is later. But what I mean, low frequency, low temperature. How do we extract information from the self-energy? Well, the first things we can extract is the location of the Fermi surface. So, what is the Fermi surface in an interacting system? Question. Anyone? No? Yes? Yeah, you have a pole of the green functions. Similar. You have a pole of the green function at omega equals 0. Why? Because what we saw before, I mean, the spectrum. Is there a way just to go back to the Michel? To the, not one by one. Yeah. Because at omega equals 0, when you are going to cross, your peak is going to be infinitely big, your green function is going to be infinitely big, you're going to have a pole, and that's where the location of the Fermi surface is going to be. And that's important to realize because how would you define the Fermi surface otherwise? You know, in a non-interacting system, you can just pile up electrons because the many-body states are just one-body states, which is then pile up from low energy on the bound level to the very high energies, just to the Fermi surface. But in an interacting system, it's not true. This picture is completely wrong. Your many-body state is not a product of one-body states, far from the Fermi surface. It is asymptotically close to it if you look at its property close to the Fermi surface, otherwise it's not. So we need a definition that is not the same as the independent electron systems. So the pole of the Fermi surface, we look at the formula before, here. Where is the pole? Well, when mu minus epsilon k minus real part of sigma k r at omega equals 0 is equal to 0. As we see, the self-energy in its real part at 0 frequency encodes the renormalization of the dispersion here. You can view that as an epsilon tilde if you want. That gives you the location of the Fermi surface. Usually, well, sometimes it's not very big. Sometimes the interaction can drastically change the Fermi surface. And if you want to see a beautiful picture, you can ask Michel in his recent work about the Hubbard model with exact solution with diagrammatic Monte Carlo, where we can see really that this effect can be quite large. So the first thing, the Fermi surface. Good. Now, we are going now to extract the rest. At low frequency and low T, I am going to say that the self-energy of omega is going to be the real part of the self-energy at Kf plus, well, a first order in omega, and I'm going to call it like this because the first derivative of the self-energy at the Fermi surface at k point will be the quasi-particle residue Z, Zk, plus some term which is, so I'm locating myself at the Fermi surface here. For simplification, I will just write the formula for a spherical Fermi surface, but it's about the same in general. Just simplify a bit the notation. K minus Kf times dk, real part of self-energy at Kf, and at omega equals 0. Ah, no, that's too late. No, that's not what I want. Okay. Real part of self-energy at Kf at omega equals 0. If you have a general Fermi surface, what matters is the derivative across the Fermi surface. So you have to do the derivative orthogonally to the Fermi surface, plus an imaginary part of sigma at the Fermi surface as a function of omega. So I'm just doing an expansion. And of course, in a Fermi liquid, the self-energy is regular. That comes back to your question. The green function will be singular at the Fermi surface. The self-energy is regular. It has a nice expansion like that as a function of k minus kf on omega. And the imaginary part of self-energy here as a function of omega at small omega and temperature goes proportional to omega square plus pi square. That's where the gamma the square behavior close to the Fermi surface will come from. This result is not trivial. It's just a phase space argument in the Fermi liquid. You have to really prove it, either in perturbation theory, but that result is in fact general at low frequency. It's not limited to weak coupling. So you have this self-energy here. And now from there, well, we are going to extract the quasi-particles properties. I just need one little piece, an addition, which is the fact that epsilon k itself, I'm going to expand it close to the Fermi surface by saying k minus kf over some mb, which is, okay, so what is this? Any idea? That's a dispersion that's close to the Fermi surface, and I expand close to the Fermi surface. Yes, exactly. That's a bond effective mass, MB, non-interacting. All right, so then what I do is that I take the inverse of my function gkr of omega minus 1, and I write omega plus mu minus epsilon k minus real part of sigma k at kf minus k minus kf. No. Yeah, well, write it below. Minus omega times 1 minus 1 minus dk minus imaginary part of sigma minus the term I'm looking for, k minus kf, times 1 over mb plus dk of sigma at kf. I'm just putting back, what I have for sigma into the green function. And the point here is that you're going to eliminate this omega term, and what you're going to have is omega over zk. That's not great. You would like to have a function which is 1 over omega, so it's going to be zk over omega. So your gain function is going to be GKR of omega equal ZK over, by just rewriting this term, K minus KF over M star minus EI gamma K. That's an important formula. And I'm going to give you the expression of Zk. So Zk is 1 minus d omega sigma k at omega equals 0. That's what minus 1, that's what we saw before. Mb over M star is equal to Zk times 1 plus Mb dk sigma kf at omega equals 0. And gamma k is Zk times imaginary part of sigma k at, well, so you see that the self-energy with these different derivatives contains the quasi-particle residue, this term here, which is the effective mass, the first term, Mb, is effective mass due to the bound curvature, but here we have two effects. We have another effect which is due to the interaction, the self-energy, and will give you the effective mass or the dispersion of the quasi-particles, and gamma, the lifetime, which we saw before, is here. Note that gamma is not just the imaginary part of the self-energy, but multiplied by z. It's an error that many people often do, to forget that there is z factor here. So you see that from the self-energy, it's quite rich object. Its frequency dependence gives you the quasi-particle residues. Its k-dependence gives you about effective mass. Its imaginary part gives you about the lifetime, everything which you wanted to know about the quasi-particle peak.
Really?
Yes. Yes, sorry.
I have a question. There's a partial derivative by k of sigma of k Fermi.
No, that's... So it's a partial derivative with k. It's a typo at k equal kf. That's what I meant.
Is the quasi-particle weight the frequency derivative of all of the self-energy or just the real part?
The real part, because the imaginary part will be 0 anyway. Yes? So, if I go back, Michel, how do I go back to the pictures of all the... Non, pour revenir en arrière. Oui, mais the next one. I'd like to go have the pictures of all of them. Ah, okay, good. Yeah, this one I wanted. Good. So we have all the characteristics of the quasi-particles, and most of the stories of strong correlations is the fact that a lot of the spectral weight, which was without interaction in the peak, is going to move to high energies, or something of the of order U, of the order of the atomic excitations, and what will remain is a lower quasi-particle peak here, which will be encoded in the self-energies. So there will be two parts in this functions, a universal part at very low energies that describe the Fermi liquid property here, and a high energy part which is an atomic excitation that we want to have. And the stories of correlations, we'll see that tomorrow about the mode transition, is how you transfer spectral weight from one to another, how these two structures compete with each other. And DMFT, just to anticipate a bit, because it's an approximation of these kind of functions, we'll be able to see the competition and describe both the high energy structure and the low energy universal structure. That's what I'm going to elaborate on in the next lectures. So I would like to finish this chapter by just drawing a picture and saying how is the self-energy, how does it look like? So oh, why is it blue? Okay. So I like to make a picture. Is there any way to go a straight line here? Okay. So going to plot the real part of the self-energy and the imaginary part of the self-energy. So the real part of the self-energy will go like this. Maybe I should use color. No. Sorry. That, and the imaginary part of the self-energy will look something. Like that. So, in the real part of the self-energy, here, close to omega equals 0, you will have the slope. The slope, as we have seen, is going to give me the quasi-particle residue at 0 frequencies. Here, I'm going to have, at 0 temperature, something proportional to omega square. My imaginary part of self-energy is going to be proportional to omega square. But what matters is that there is an energy scale somewhere here, which is this coherent scale, below which the Fermi liquid theory is valid, above which it's not valid anymore. Fermi liquid theory is an asymptotic low energy theory. It's valid below some coherent scale, which is a coherent scale of the Fermi liquid. Now, what happens at high frequency, this goes to 0, but this goes to some constant. Why does it double this? It goes to some constant, which is typically the R3 term, not typically, but plus a constant over omega. That's the asymptotics. So in a Hubbard model, for example, the R3 part is going to be U times N, the number of particles down, for self-energy up. So that's just the R3 approximation. But what's important here is that the Fermi liquid theory is valid here at low energy. But it's not valid above that. And I will show you pictures tomorrow when we solve that in impurity problem, where we can see that these regions can become quite narrow. So you should be careful when you look for Fermi liquid behavior. Okay? It's really an asymptotic low energy theory. And in some cases, for example, close to a quantum phase transitions, as a function of some parameters, this coherent scale may just collapse and vanish at the quantum phase transitions, right? Therefore, you will have an intermediate, very low frequency regimes with Fermi liquids, an intermediate regimes. Antoine Georges, in the second lecture about DMFT will show you Hund's metals where you will have an interesting intermediate regimes, and then you have the high frequency regimes. Okay. So that's what the self-energy looks like. I'm going to make it slightly smaller in real frequencies. Good. Finally, I want just to say one remark about sigma in an insulator. Because I said the self-energy is great, you can extract a lot of physics in the Fermi liquid behavior, but what about an insulator? I mean, the self-energy is well defined. You can define the self-energy because it's the inverse of the Green function, so no problem. If you are not careful, you can just plot the slope of the function, extract a z, and be happy, except you are an insulator. Yes, this has nothing to do with the quasi-particle residue or anything. And so what happens in an insulator? How do we think about that? The simplest way is to take the caricature of an insulator, an Hubbard atom, one atom, as we saw before. If we have the Hubbard atom, so again, putting it here, and up -1/2, and down -1/2 times u, I write it in the particle hole symmetric case. We have, remember, the spectral function is 2 peaks, so we have a gap of order u. So that's, okay, so what is the Green function here? We wrote the spectral function before. The Green function is, retarded function is 1/2 over 1 omega minus u over 2 plus 1 over omega plus u over 2. Very easy calculation. So I can compute the self-energy, right? Because I know the bare Green functions, and I will find that this is 1 over omega minus u squared over 4 omega. That's the self-energy. One hour. Yeah, what? No. 10. Yeah. Sorry, what I was, yes. So the self-energy here, as you can see, the self-energy diverges at omega equals 0. It's very singular. So you can define it in an insulator, but it can be singular. However, it does not necessarily diverge. It does diverge in this very specific case. In other cases, it will have poles in different places. So as soon as you try to extract physics and self-energies in insulators, be careful, because, it may not be as, meaningful as you think it could be. So it can diverge, it can look like a reasonable self-energy, but I'll show another example with the Matsubara in a moment. All right, so is there questions about that? So my point here was remind you about a couple of Green functions, spectral functions, how do you extract physics of Fermi liquids, and you will use that in the result of DMFT to extract, Fermi liquids properties in this. Yes?
You mentioned that sometimes the self-energy will look normal in insulated. The normal doesn't mean that it approaches 0 as omega goes to 0.
Normal, you mean?
You just see that the self-energy diverge in
Yeah.
insulator as omega goes to 0.
In some insulator, yes.
Right. And in others, they just go to 0.
Yeah, they can go to constant, because your pole may be at 0 like it is here, or it can be shifted if you just shift the chemical potential. So if you look at it, especially in Matsubara, I'm going to replot it later, it look perfectly normal. So I will re-insist on that in the Matsubara case, which is even more drastic.
So the Fermi liquid equations we wrote down just earlier, you said they were valid for low omega and low T.
Yes.
But are they also only valid when we have a general well-defined quasi-particle peak, or are they more generally well-defined and used for this?
Question?
This insulator.
Yeah.
Is this well described by the equations we just wrote down previously?
No. I mean, the expansion of the self-energy. The self-energy may not be regular, have a nice expansions in away from a Fermi liquid.
This system is also low omega, low temperature.
Yeah.
So the difference between the two is that one
The
is.
system is in a different phase. It's a different system.
Oh,
Yeah. If you have a Fermi liquid, the self-energy is regular, you can do the expansion, sigma imaginary part is omega square, and then you can extract the physics. If you don't have a Fermi liquid, the self-energy exists, you can plot it on a computer. You should not interpret it as a Fermi liquid in that case.
okay, so the previous equations work when
Fermi liquid.
for Fermi.
Fermi liquid. That's what I wrote. Good. So now I'd like to do the second piece. I need to tell you a bit about Matsubara green functions. What happens? So, we are going to work in imaginary time. Tau between 0 and beta, which is 1 over the temperature. I put the Boltzmann constant equal to 1 here. So even though it's called imaginary time, tau is very well real here, but it's a matter of semantics. For any operator x, we are going to look at the time evolution x of t, which is e to the h tau times x h tau. So that's a time evolution, except contrary to the time evolution which we had in real time, which suddenly I fear I forgot to rewrite, but nobody said anything, so it was, I guess, obvious. In real time, this is, of course, with an I. Here we don't have an I, right? And this is with real tau. Beware that when you do manipulations, the dagger of this is not that. That's a common problem when we do this time evolution. So we do a time evolution in imaginary time from a time that goes to 0 to the inverse of the temperature. That's quite common in statistical mechanics, where we consider the thermal evolution to do the thermal ensembles from 0 to beta. Okay, so equipped with this definition, and here we are going to assume that H is such that the energy of the ground state is equal to 0, just to avoid any annoying problem here, or we can of course eliminate it, but it will just make it slightly easier. So the definition of the Matsubara green function is similar to the one I was using before. Note there is no R here. I put nothing because I'm going to use it a lot. This is minus the time-ordered operator between Ca of tau, Cb dagger of 0. Ah, no. not 0, tau prime. And this is not a minus, this is not nothing here. That's the definition of G. Now, the time-ordered operator is such T tau is a time-ordered operator which is defined such that T tau of two any operators A tau, B at tau prime is such that, just to write it correctly, theta function T minus tau prime, A of T, B of tau prime, plus zeta AB T tau prime minus tau, B of tau prime, A of tau. So it's an operator that will put the two operators in order. If the time are decreasing, it does nothing. If the time are not, it put them back into a decreasing order. That's the meaning of these two theta functions. Zeta is equal to 1, except it's minus 1 if the two operators are fermionic. In our case, with C and C dagger operators, it will be minus 1 because fermions do anti-commute. Okay. So G tau, and that's a point which is often missed, is defined because it's defined as a function of tau minus tau prime, and tau prime going from 0 to beta. It's defined really on minus beta beta. So we define it as 2 beta periodic on R. So you have a function that's defined on minus beta beta. You periodize it on 2 beta. That's your definition. And then you can prove the following relation. You can, in fact, prove that G of tau is, we're talking fermions here, beta anti-periodic, will be periodic for bosons. And the reason is that if you take tau less than minus beta 0, using the definition, you can prove that GAB of tau plus beta is equal to minus GAB of tau, using simply the definition. So the function is beta antiperiodic. Has everyone seen Matsubara green functions before? Yes. Who wants me to do that? Because if you have already done it, there's no point. It's short, but you know, it's on demand. You know that. Perfect. Yes?
The last relation that you wrote down holds true for bosons and fermions, but not for real fields, right? If I have a phonon displacement or something like that?
That's for fermions.
Okay.
For bosons, there's no minus signs. Okay, so very good. So now, as we know, we can go to Matsubara frequencies. And just to fix notations, we'll use omega n equal 2n plus 1 pi over beta for fermions. And for bosons, well, I'm not going to use bosons, so, but you know, it will be that for bosons. Not critical for us now. Because our function is 2 beta antiperiodic, it has a Fourier series representations using these frequencies, which are the Matsubara fermionic frequencies, And to fix all my conventions, I'm writing the transformations. That's also the convention that will be used that's the one that are used in tricks and in the tutorials. The function of tau is 1 over beta, sum of n in z, exponential minus I omega n tau, GAB of I omega n, and GAB of I omega n is equal to integral 0 to beta d tau e to the I omega n tau. These are the two transformation relations which we will need to use. Check and not make some typo. Good. So I leave you that as an exercise. If you don't know how to do that, ask me. I'll show it or show it later. All right, so now the thing we need is to relate those Matsubara-Green functions to the real-time function we had before. But the first question is, why do I care about Matsubara-Green functions? And the reason is that many of the techniques of solutions, especially Monte Carlo techniques, but not only, work better or just work in the Matsubara domain, in Matsubara time. And of course, all of the experiments are done in real time, not in imaginary time. So we'll have always to play this game, which is a delicate game, as you will see, between the imaginary time and the real time. It's easier to compute in imaginary time, but we want to get back in real time. And of course, it's hard, because you have much less information in imaginary time. Monte Carlo will have a lot more problem in real time. Even though it's doable these days, it's still much more complicated. So we need to, in many calculations in the solver that Michel will describe tomorrow, or day after tomorrow, you'll get out in your calculation a result in function of tau or I omega n. And so we need to play the same game as before. What is the relationship with the physics? How does it look like? What does the function g tau look like? How am I going to recognize an insulator or a metal in this framework? Sorry. So the first point I need is to relate this function to the spectral representation. So I'm going to give you two results. Again, if people are interested in the detail of the derivation, I've redone them, but I can give them to you on a set of notes. I'm going to do two things. First, I'm going to write Lehmann representation at finite temperature. When I started earlier, I did it at 0 temperature. I'm going to give you the formula at finite temperature. It's exactly the same, except you are not in the ground state. You have to insert two states to break the trace, not one state. But you'll get this formula, 1 over z, sum over AB, A, CA, B, B, C dagger A, times some thermal factors, which are just there to do something very specific. So you have now a sum over two sets of eigenstates on the many-body states, big A and big B, simultaneously. And of course, if you take the 0 temperature limit, you will see that you project this or this to the ground state, and you get back to the formula that I had before. Okay? That's good. Again, that's the retarded Green function I had before. It was defined at finite temperature. I can do the calculation at finite temperature, no problem. Now, what I'm going to do is to take the Green function GAB of t. And that function is CA of t CB dagger And what I'm going to do here is the same. I am going to insert two operators, A and B, and do a decompositions and obtain the following results if I do that. So I'm going to obtain GAB of tau equal minus over the sum over AB of exponential minus beta EA. A, that's the same as before. Just the same as before, so it starts to look the same. Well, it's not exactly the same as this and that, but it looks similar. We have the same terms. And then what we do is that we go to frequency space, and because you have to be slightly careful when you do the integral EI omega tau plus EA minus EB times tau, these things give you minus 1 plus EA minus EB over I omega n plus EA minus EB. Because you integrate, so you get 1 over omega n minus EB, but you have to be very careful because at 0 it gives you 1, but at beta, e to the I omega n beta gives you minus 1. So it gives you this intermediate results. And that allows you just to do the Fourier transformation and compute the Green function in imaginary frequencies. And you will find out, if you replace this into that, you replace this integral into this, and compare to that. Just take a piece of paper and do it. You will get the following results. GAB of I omega n is equal to the integral d epsilon of A B of epsilon divided by omega n minus epsilon. And that's a very important result because it tells you that, I'm going to write it in time as well, GAB of tau equal minus integral d tau of A of epsilon exponential minus epsilon tau 1. Oh. Plus exponential minus beta epsilon. So the important part is that you get the Matsubara-Green function here in imaginary frequencies. It has the same spectral representation we had before for the retarded Green functions, except the omega plus I0 plus is replaced by I omega n. And the Matsubara representation is chosen exactly to have this property. That's why you take the two beta periodic functions and all of these, because a priori you could take something different, in imaginary time, and because of the choices of the definitions, we'll have exactly that relation. So the immediate consequence of that is the fact that we have a way to go, at least formally, to go from the Matsubara, which we can compute, to the A of B, which we would like to have in the calculation, and that is analytical continuation. So I like to do that before the break and write two things. No. I want to take that. How do I do it again? Je prends ça? Ah. Voilà. Et après? Ah. Ouais. Okay. Non. that will be okay. I just needed this one. I just don't need this one. Okay. That's what I want. First thing, before I want to do that, I want to have code the results for free electrons, which we will need it. Free or independent electrons. You can check that in case you have H equal sum over epsilon k, C dagger Ck, your Green function Gk over I omega n is going to be 1 over I omega n plus mu minus epsilon k. And in general, if you have an Hamiltonian which is the sum of C dagger A, M, A, B, C, B, meaning a matrix, G of I omega n is equal to I omega n minus M minus 1 as a matrix. It's a simple exercise to show these things that by replacing into the like we did for the Lehmann representation, for example, this by diagonalizing the matrix and changing the basis into a diagonal basis for M. So we will use these two results in a moment, but I want to finish by commenting on this before we break. This gives me, and I'm going to rewrite, oh. No. What has happened here? Michel? Why is it suddenly writing like this? Huh? Yeah, I'm here. Ah, so painful. Okay, well, let me take another one, sorry. You know, I'm going to write it again, and it will be simpler, because frankly, this board is not so obvious. I'm write it again, it's just worse. Okay, that's what I want to compare. And here, we have the same A between the two. So that's what you will see in many books. Sorry. I am again saying, okay, we can do an analytic continuation. Which is to say that you compute this and you send that to omega plus I 0 plus, and you're done. You go from one to another. Well, that's certainly true in analytical calculation, even though even there you should be slightly careful in some cases. But if you do diagrammatics to first and second order, you can take your expressions when they are properly written like that, and you can do these continuations and get back to the real axis. However, in our problems, in numerics, this is much harder than this. And the reason is obvious if we look back at the other expression. Which was this one, is that this G of tau is the Laplace transform of A of epsilon. If you want to inverse that to recover A of epsilon from G of tau, you have to do the inverse Laplace transform. And as soon as you want to compute an epsilon which is relatively big, this exponential here will kill you. In other words, the rank of the matrix here is very small, so inverting this relation is extremely difficult. So there are many ways that people have been trying to do that, that you will find in the literature and in the techniques, and we'll see some of them in the tutorial, but I'd like to insist on really the methodology here when we're talking about analytic continuation. First, we are going to extract as much information as possible from Matsubara data. And that's really the key. That's number one. You're going to try to understand your system, understand its physics from the Green function in Matsubara data, because that's by far the safest things to do. If you can't do that, and so the question is, what can you extract from the Matsubara data? All the static correlators. These static correlations, for example, NK, C dagger K, CK, the number of particles, the thermodynamics, the low energy behavior. I'll show you an example later. That's okay. What's hard or impossible is the full A of omega. You can do it approximately, but it's difficult. As soon as you want to do transport, that's also difficult. And also regimes where you have frequency less than the temperature, because your first Matsubara frequency is at the order of the temperature. So if something happens in your frequency below the temperature, you have to reconstruct it by doing the analytical continuations. So there are many things you can extract from Matsubara, and when it's possible, extract information from Matsubara. Second, solve in real frequency, if you can. There is a lot of effort to have techniques of solution in real frequencies. And third, if you can't do any of that, you use analytical continuation. Technique, which means technique that takes G tau, recovers A of omega or A of epsilon, at least some approximation of it, but as I said, it's an Hilde-Pose problem. It's an inverse Laplace transform. There is no way to control that fully. There are a couple of candidates. You will use some of them that are doing a good enough job, but should be used with care. One is Padé. I think you use in one of the tutorials tomorrow. The other one is Maxent, which is well suited for systems with stochastic noise, where you have stochastic noise in G tau. I don't know if we will have a Maxent in the tutorials, but yes, there is, yes. And there are a lot of new ideas which have been put forward recently, for example, Nevan-Lina techniques and others. But, and all practitioners may not fully agree with me here, but that's my, and now it's all frozen. That's my way of thinking about that. First, you extract the physics from the Matsubara framework. Then you try to solve in real frequency if you really need to. And then if you can't do these, then you do analytical continuation. Because it's a dicey game, and we can easily see that you can make mistakes in doing that. So we'll make a break. After that, what I will do is finish on the Matsubara, by telling you a little bit how the Green function look like, where to find a metal and an insulator in these, and then I will talk about quantum impurity models.